Hi everyone, welcome back to Sarah, and today we are joined by Professor Dung. Thank you so much for doing this.
Thank you.
First, congratulations on receiving the Fields Medal at this week's ICM ceremony. What has this week been like for you, and could you please tell us a little bit about your work?
It's a really busy week. So I remember on the day of opening ceremony, I had all the whole morning kind of completely occupied. And when I kind of finally got back to my hotel, I realized I have almost 100 unread emails. So it was really nice, nice feeling. It was really exhausting at that time. But yeah, and especially I feel that now I'm getting really famous on Chinese internet, which is I don't know how to say about this, but it's yeah.
And what was that whole process sort of like? Because obviously the Fields Medal is a huge award. Could you predict that you could have won this? Was it something you ever thought about as you studied math?
Well, yeah, I maybe had some vague thought about it, years ago. I mean, I at one time I was really seriously thinking about it. Like in 2024, we finished that work, so I was thinking, maybe that's something. But really, I learned this only in January this year. So, I really haven't been thinking too much. Although I mean, when the time came close, I was get a little bit stressed, not too much, but yeah, really, I mean, usually I don't think about these things because these things you cannot control.
I think that's a great answer. So part of what your medal recognizes is your breakthrough work related to Hilbert's sixth problem, a challenge that stood for over a century. So in terms that a general audience or I can understand, what did you and your collaborators prove?
Yes, essentially, I mean, it concerns this picture of the fluid or the gas kind of that is made up by these tiny particles, tiny molecules. So what you want to do here is that you want to connect these the kind of the behavior of these particles, which is very relatively simple. Like you have Newton's law, you have interactions, kind of binary interactions, and you kind of start from this huge system and you try to find this effective equation that governs the the kind of statistical behavior of these particles, which will be the Boltzmann equation, and then with the second limit you get to this familiar fluid equation. So this is kind of the main thing that we did in terms of building this bridge between the different scales.
As a high school student, it's sort of crazy to see all of the amazing things that you do in your everyday life. So, how did you get from school to where you are now? Was this something that you ever saw yourself doing as a child, or what was sort of your path to get here?
Yeah, so when I was in high school, yes, I was in this IMO and I got a gold medal. That time I was kind of thinking that maybe it's the math is the correct thing for me to do. I mean, I don't think there is a particular moment where I decided on that, but it was kind of gradually because after the IMO, I decided to learn some analysis, kind of college math, and then I went to college and I keep enjoying doing math. So gradually I realized that this is this thing I want to do.
I think that's a really cool answer. At the heart of your work is the challenge of explaining how order emerges from randomness. You said that there's an enormous amount of randomness in the world and that mathematics needs a way to capture it. What does it actually mean to track randomness across billions of colliding particles and interacting waves and then derive predictable laws from it?
Yeah, so it's the picture is yeah, there is a lot of randomness, but then okay, so on the one hand, randomness means that there is uncertainty. On the other hand, you don't need to keep track of every single trajectory because you have randomness. You only need to keep track of what happens with high probability, and that actually simplifies things a lot. That there are always kind of exceptionally bad cases like that happens in this dynamics, but if you don't need to care about those, you only care about what happens generically, then usually this will be much better than the exceptionally bad cases. And so yes, this is idea, and of course you need to discover some ways to estimate it. You need to justify that these bad things really happen very with small probability of happen very rarely. But this is something you need to do, but it's in the end, it's there's something you expect to be true. Yeah. So, but on the other hand, there are also kind of very difficult questions that we still do not have enough understanding in terms of randomness, like the propagation randomness, for long time scales and things like that. It's still something very difficult.
So it's like almost probability, or
Yeah, it's essentially probability. Yes.
I took biology last year, and I'm starting to realize randomness has a huge effect on our lives. Like in biology itself, there's entropy and diffusion, and I could see how randomness affects every single branch of science and mathematics. So, what do you see some applications of your work being in the future?
Applications. Well, I mean, yeah, if there is a better understanding of these structures that we are seeing in these derivations, maybe there could be some applications. I mean, for now we are kind of more kind of in from taking the point of view of pure math kind of proofs. But yes, I mean, who knows? Maybe there will be some applications if we understand it kind of better.
I think, as I talked about before, I'm a high school student, and so when I think of math, I think of like slopes or graphs or addition, subtraction. How do you get to that level of pure math, and how do you find the next problem that you're going to work on?
Yeah, I mean, yeah, in some sense, like math is a combination of these basic objects. Yeah, it's also a way of understanding nature. So this is what is amazing, that you can use this combinations of these really simple things to find a way to understand nature, which I think is really amazing. And for the next step, well, there are many questions. So one question I've been thinking about is this propagation of randomness for long times, and then also a number of so-called critical problems in PDEs, SPDEs, quantum field theory, that hopefully some method we develop will be able to will be applicable. And well, there are really like many interesting questions to look at.
I think that's really intriguing. So, you mentioned that there is still a lot more to learn in mathematics. So, looking into the next ICM in 2030, I think, what would you hope to see, or what discoveries do you hope to be made by then?
Yeah, I mean, I hope in this direction of quantum field theory, I hope to see maybe there will be some maybe significant progress, because I think there are already starting to be some tools like in this subject. And yeah, so I would hope to see there is some maybe significant progress in this direction.
Mhm. Your work shows how new mathematical techniques can make previously unreachable problems accessible. Today, AI and formal proof systems are expanding that toolkit even further. How do you see these mathematic technologies changing the way that mathematics work?
Yes, so yeah, AI has been more and more helpful in the math research. I mean, so for the future, I would expect I'm still in the progress of learning how to use AI, learning how to effectively use AI. But I think one of the things is that AI now can solve some kind of short theorems, can prove some short theorems, and then I would imagine, like, if we working on some big project, and we can have a framework that allows us to divide this project into like a few like individual sub lemmas that is relatively short, then AI probably can help us prove it, and which would significantly kind of accelerate the progress. And I hope that this would make kind of the progress of the doable things faster, and will make kind of currently undoable things doable.
You mentioned how you are still in the process of learning how to use AI, and I think that that's a place where me and lots of everyday people and even mathematicians are. So, what was your original reaction when you first, I guess, used AI, and where do you see it going in the future?
The first time I actually seriously used AI in my research was so there was a lemma like in my research project recently, and I spent like 5 days. I found a proof, like 4-page proof, but I asked GPT, and it gave a 1-page proof in the like within 1 hour. So I was really impressed. So yeah, so in the end, it turns out that that proof cannot be kind of generalized because the question I asked here was a special case, so we didn't actually include it in the paper, but at least it provides something very useful, some ideas that is very useful. So I think yeah, I'm sure AI will get stronger, so it will, which means it will be more helpful. So yeah, so there are also kind of concerns that if AI can produce like even longer proof, like even more complicated proof, then what do mathematicians do? So my point of view is that okay, so right now we prove theorems. Okay, so we're going to rely on the know the theorems that we know. Okay, we rely. So if AI can prove some more theorems, then we will rely on those theorems as well, and we'll build our arguments, build our thoughts on those theorems, provided we can understand them, and we'll investigate further things. So in this in this aspect, I think. AI will always kind of be something that is helpful. I mean, I wouldn't say it's helper or assistant or replacement or anything. I don't want to view it in this way. It's not we're not competing against AI. We are working with AI to achieve things that we previously cannot achieve. As long as we can do this, then there is nothing to worry about.
Earlier in this interview, you talked about how pure mathematics and advanced mathematics is sort of just high school math piled over and over itself to become more and more complicated. And just now, you sort of mentioned how if AI proves more theorems, that just expands your toolkit further. So, where do you see math going even further in the future when these discoveries just pile on top of each other?
Yes, I hope that also said this sentence earlier that I hope the acceleration by AI will make the previously impossible questions possible. So then we'll really be able to advance like much further than we had imagined before.
After solving a problem connected to a challenge that is more than 125 years old, where do you go next? What question or broader mystery would you most like to solve now?
Yes, it's so really one question I mentioned earlier is this long time kind of almost sure global hypothesis problem, which I think there are some ideas, some vague ideas, but I'm not sure how to make that work. But that's something. And another thing was this quantum field theory I mentioned, which I really expect to be there will be at least some progress like in the near future.
What is this quantum field theory that you mentioned? Could you sort of go more into detail about that?
Okay, so it's really concerns kind of construction of a certain kind of infinite-dimensional measures, and the most kind of like the most famous problem here will be the Yang-Mills construction of Yang-Mills kind of theory. In an elliptic version, it's a construction of a measure, but it's really complicated, and there are different ways to approach it, and the reason it's complicated because it's a so-called critical problem, and so I hope that the method, the problem we had been working on, this wave turbulence, in some sense, are also critical problems. So I hope the method developed might be kind of helpful. Of course, it's still pretty far away, but I think at least we have kind of a roadmap, and we probably have we're starting to have some the first basic tools for that, and yeah, I wouldn't say like we are close to it, but with AI, like maybe there is nothing that is impossible.
The first word you said with that was interdimensional, and to me, that is such a crazy topic. Like, how do you even envision that? How do you think about concepts like that? Would you say it's more mathematical? Like, do you envision equations, or how do you even grapple with something like that?
Yeah, it's like you have in 5 dimensions your your points is determined by finitely many coordinates. Now, infinite dimensions, your points is determined